Let me share my screen. Can you see my screen?
Yes, Dr. Ali, we see it.
Okay, great. So everybody see, like today's topic is synchronous machine representation in stability strategy. I mean, from now on, we are gradually going deeper into that stability concept. So today we'll be looking at physical description of synchronous machine in terms of d-axis and q-axis. So I'm coming that one. So d-axis means direct axis. Q-axis means quadrature, which is in 90-degree phase shift than the direct axis. So I am giving the definition, what is the meaning of that. And then mathematical representation or description of synchronous machine in terms of, it is called dq0 or Parkes transformation. I mean, this is very important and very famous transformation theorem in power system. So I'll be discussing that and then followed by some questions and numerical problems. So today you all need the calculator so to solve some problems. So therefore, first of all, what is that concept, d-axis and q-axis for the synchronous machine? So let's have a look at that. So everybody, I think you can see. This is the picture I have taken from that Prabha Kundur's book that I'm following, figure number 3.9, stator and rotor circuit of a synchronous machine. So everybody see, like as we discussed before, synchronous machine has two main components. One is called that stator, on which the three-phase coils are placed, and then the other is the rotor circuit. On the rotor circuit, there will be magnetic field, and that magnetic field will be connected to the shaft, and that shaft will rotate. This means magnetic field will rotate. Now, you can understand this arrangement. This is just a three-phase coil mounted on the stator body. But here you see there are two things. This is on axis. It is called, you see, the D axis. And then 90-degree ahead of that, 90-degree leading of that, that is the Q axis. So therefore, I mean, before discussing this on much more, first of all, what is the definition of D axis and Q axis? Everybody see here at the beginning of the next slide. D axis means direct axis, which is centered magnetically in the center of the North Pole. And then quadrature axis, 90 electrical degrees ahead of that D axis. That is the definition. So this means D axis is centered magnetically in the center of the North Pole. So you know magnetic field means it has the North Pole and South Pole. So that is the meaning of that. So now moving forward, what is the goal here? So first you see the location and then I am telling its physical significance and meaning. So the thing is that this is the main field winding which is placed across the d-axis. That is the definition I told, that centered magnetically in the axis of North Pole. This is the actual magnetic field. And you see there are two other coils. One is in parallel or in phase with the main magnetic field. It is called KD. And then with the 90-degree, I mean, from here 90-degree leading or from here 90-degree lagging, that is another coil. These two coils are the damper winding. Everybody, can you remember that I mentioned in case of synchronous machine, they have damper winding. I think I discussed in case of a synchronous motor that without damper winding, synchronous motor can't start. But damper windings are used in case of synchronous generator also in order to eliminate the hunting effect. Hunting. Hunting means some sort of undesired oscillation that occurs on the shaft system of a synchronous generator because of the continuous change of load, a small change. Like because customers are continuously changing some load, then frequency is never ever 60 hertz we discussed, and that has the impact on the shaft system. That always like little bit oscillates. And then sometimes you might see some sort of weird sound or humming sound from the synchronous generator. In order to eliminate that effect, humming effect or hunting effect, those two damper coils are placed on the synchronous generator. This means damper coils are placed on both synchronous generator and synchronous machine. So that's why you see, and they are placed on the rotor circuit. That's why on the rotor circuit, you can see three coils. So keep in mind, this is the main field coil. You see, current is designated by the symbol IFD. FD means field winding. And then these two are for the damper winding. So here you see, in the book, it is mentioned in terms of this KD and KQ. Those two are the D-axis amortisseur circuit, Q-axis amortisseur circuit. Amortisseur circuit is the same as to the damping circuit, damper. So in literature, so this word is used, amortisseur, instead of the damper winding. But in many other literatures, damper winding is used. And then that FD is field winding. Now, what is the main goal here, or what it explains, or what is the physical significance? So the goal is that you all know, if you see the stator, once voltage is developed on these three coils, and then the current is going towards the grid, that IA, IC, and then IB. So you all know that those IA, IB, IC, they are the sinusoidal. I mean, for example, IA equal to Im cosine of omega t. IB is Im cosine of omega t minus 120. Then I say Im cosine of omega t plus 120. So you all know that those are the time varying function and sinusoidal function. Now, when you see that this system will be connected to a huge interconnected grid. Now, if you always deal with the time function like cosine omega t or sine omega t, it is very difficult to find out power flow on the current or specific branch power, reactive power, etc. If you always deal with the time function. That's why there is a system that you can express these stator quantities, time varying quantities, in terms of the rotor field circuit and then damper circuit quantities, just with the help of the theta. And you can make those time varying quantity independent of time. Only they will be functions of theta. So that's why the goal of this figure to place side by side to establish a relationship between the rotor circuit component and stator circuit component. And then the main goal is that how we can transfer or how we can make a relationship of these three components, IA, IBAC or VA, VB, BC, in terms of the D-axis and Q-axis component. In other words, the D-axis and Q-axis meaning that three-phase system can be transformed into two-axis component, provided that the total magnetomotive force here in this for three-phase system and total magnetomotive force for the D-axis and Q-axis system remain the same. Then that relationship holds or that relationship is valid. So therefore the goal of this study is that we want to show the relationship of IA-IB-IC in terms of ID and IQ component. This means everything in three-phase system, we want to convert those time domain or the time dependent function into time independent function, and we want to represent only two axis system, which is D axis and Q axis. So now the question is, how is it possible and how we can? So therefore you can say there are a lot of equation and you will be getting that. So the other thing before going that, see the definition. Here I have put on theta. So therefore you clearly understand that D axis and then Q axis has 90-degree phase shift. That is 90 degree, that is fine. But what is that theta? See what I have written, axis of phase A. So this means that we said that D axis is centered magnetically in the axis of North Pole. So that is the D axis. And then this is the A phase, A axis. What is the phase difference between this axis and this axis? That is the theta. I mean, why it is? Because you see, because this is, you see, rotation, direction, omega or electrical radian per second. Ultimately, you know, the rotor circuit with the help of the prime mover that is moving. So that's why there is theta. So therefore, at an instant. Now, the thing is that there is theta with respect to f phase and the d axis. Similarly, there will be phase difference or similar theta with respect to b phase and d axis, and the same thing goes for the c phase and then that d axis. So now we want to make a relationship with this system and with this system. And then, as I said, goal is that to decompose or to convert into this three-phase system into the two-axis component. That is the goal of this study. And that is what is called like DQ0 or the Parkes transformation. So the Parkman, according to an engineer Park, who first developed this concept. He first, you know, that transferred that three-phase A phase, B phase, C phase time-dependent function into the time-independent function in terms of the dq. And then there is another thing I am coming that point. It is called dq0. So far I have talked only about the d-axis, q-axis. There is another thing which is called the zero sequence component. So therefore, the goal of this one is that to convert into three-phase system into two-axis system, provided that the total magnetomotive force among these three coils should remain the same into that two-axis system. Now, how we will make the relationship? How we can convert this three-phase system into two-axis system? That is today's discussion. Therefore, everybody see, I have written down, you see that some equation. What I said here, the rotor circuit flux linkage may be expressed as. So flux linkage mean it is expressed by the symbol psi, and psi means multiplication of current and inductance. Everybody, you note down in your paper. Flux linkage means it is the multiplication of current and inductance. So therefore, for example, you see, it is written here psi A, psi B, psi C. This is the flux linkage. What is the flux linkage of this coil? What is the inductance value of this coil? Like, for example, LA multiplied by IA. So therefore, wherever there is a coil, there is flux linkage. This means that multiplication of current and inductance. Same thing, you see, there are three coils here. Two are on the d-axis and one is 90-degree ahead of the d-axis, but all three coils have current and they have the flux. So consequently, each and every coil in this picture, they have the flux linkage. Now, here I started talking about what is the rotor circuit flux linkage that I am showing. And when I am expressing the rotor circuit flux linkage, you see automatically these things will be included. So now let's see that how those things can be included in the analysis of the d-axis or q-axis, or in other words in the rotor analysis. So therefore, everybody see, I am writing psi fd. So fd, what is that fd? First I am writing the equation for this coil. Everybody concentrate, be attentive. I am writing equation for this coil, which is the main field winding. So that's why I have written psi fd. So what is that one? It has its self flux linkage. This means its current and its inductance. So that's why you see very first term LF, FD, field winding inductance, and IFD, field winding current. Then next is the effect of, because they are in the same line, this amortisseur or damper coil. So therefore, what is its flux, what is its inductance value, and what is its current? The current is IKD, and then what is its inductance value? You see, LFKD, IKD. And then what is the effect of this one? But you see, this one is in 90 degree, and you know that these flux linkages, all flux linkages can be expressed in terms of time function like cosine theta. So therefore, because it has the 90-degree phase shift, so that's why with respect to this one, cosine 90 mean it will be the 0. That's why you see here, you cannot see any term for this coil, its flux linkage, because it has 90 degree. But now come back, these three coils. So I related all three coils, now these three coils. So what happens, everybody say, once the voltage is built up in the stator circuit and current starts flowing towards the load or the grid side, then what happens? Because of this current, another flux is created here in each coil because of its respective current. And once current is developed, then there is flux. Consequently, there will be flux linkage. But this flux always opposes the main field flux. That's why, can you see the direction? So the current is here, voltage direction here, but the flux linkage direction is in the opposite side. That is because of the Lenz law. So you all know that on Lenz law, that because ultimately this current is produced because of this magnetic field. But once current is flowing through this coil, then there is flux linkage, and that flux linkage will oppose the main field flux. That is its property. It's called Lenz law. So that's why, because there is opposite sign in this direction, you can see there is a minus sign here. That minus, and then you see the impact of A phase, which is I cos theta for phase A, this current, then multiplied by this one, this current multiplied by this one, this current multiplied by this one. So that's why LA FD I cos theta. The same thing goes for B phase and then C phase. So everybody, could you follow me what I am saying?
Yes, totally.
Yes. So therefore, simply this is the rotor circuit flux linkage equation. Now come back the other. So psi KD. Now you have to write down the equation with respect to this coil. Then again, same thing. What is its own flux linkage? What is the flux linkage due to this coil? What is the flux linkage due to this coil? And then the same thing. You have to relate with each of the coil. So that's why this is the equation. So then you look, this is also very similar to this one. But then what is that one? Psi KQ, this one, KQ, for this one. So therefore, for this one, what you can see, it's self on LKKQ, This means it's self flux linkage. But then you see, this one is in 90 degree, this one is in 90 degree. That cosine 90 is 0. So there is no term for this one, there is no term for this one. But then it is related with these coils. This means this theta plus 90 degree. So that's why you can see it's self on. And then you see there is a cosine theta, theta, but then here that theta plus 90 degree, you see, because we are analyzing this one. So what is happening? Because of that plus 90, plus 90, plus 90 in each case, those are converted into sine theta. And then because of that trigonometric quadrant, it is in the second quadrant. If you at 90 degree, there will be one minus sign, then minus minus, it will be plus. That's why you can see the plus sign here, and then all became sine theta, sine theta, sine theta. I think everybody so far is fine. And then now if I go further, so you see everybody see a pattern for this on FD and KD. This means direct access, this main thing. So for these two, they are located in direct axis. We see that all are related to cosine theta. And then this one is in 90 degree, means quadrature axis, that is related to sine theta. So therefore, from this pattern, by looking this pattern, then you can say is the flux linkage in the d-axis are proportionate to these quantities in terms of cosine theta, and flux linkage in quadrature axis are related to those quantities but in terms of sine theta. So now based on that analogy, you can make an analogy which is that direct axis component current, just simply ID, is proportionate to these components, either this one or this one, cosine theta, just proportionate. You can say ID is proportionate to this thing. In the then second line, in order to eliminate the proportionality sign, what is the proportionality factor? Which is a K. Simply you can say that. Similarly, from here then IQ, again IQ is proportionate to those all sine component, sine quantities, and but then there is minus sign because of the 90 degree phase shift, because this one is in 90 degree phase shift. So that's why you can say that IQ is proportionate to those quantity. Then after converting cosine into sine, you are getting on minus sign, and then another constant factor which is KQ. So this means that look these two equations. What it is telling? What is the significance of that? That A phase, B phase, and C phase of the stator currents, they can be converted into the direct axis current. That is the meaning. Similarly, those three phase quantities, A phase, B phase, C phase, can be converted into the quadrature axis component. And this is the relationship. So this means that summary is that we converted three-phase system into only the two-axis system. We represented that. So this means, as you can easily understand, that there is no time function here, there is no theta, only there is that theta. And then theta will be some angle. So easily you can calculate. So this means if you just know the values of the current, and then you can easily find out what is the ID and IQ magnitude. So then, like, it looks like a little bit strange that I am concluding that three-phase system is getting converted into only the two-axis system. Do you understand what I am saying? Is it not something strange that I am converting three-phase system into only the two-axis component system, which is ID and IQ? That's why after developing these two equations or these two relationships, then that engineer Park, he said, no, let's write down there can be some similarity. What is that term? I0. What is that? 1 over 3 IA plus IB plus IC. So this thing is coming from...
Sorry, I'm having trouble with the connection. Please try again in a moment.
Hello, so could you hear me, everybody?
Yes, Dr. Ravi.
Yes, sir.
Yes, it looks like suddenly some noise appeared from the Zoom system. Anyway, so everybody, do you know, are you familiar with this equation? Can anybody remember what is that equation?
That is this part.
It looks like average current.
This is the neutral current.
Oh, yeah.
You see that this is like Y connection, right? So therefore, if you have a neutral line, then what happens during any unbalanced fault, during any unbalanced situation, current is started flowing through the neutral. That's why the neutral current is this one plus this one plus this one. But that probably I told that when there is any unbalanced situation, that time zero sequence current will flow. Can you remember that I mentioned positive sequence, negative sequence, and zero sequence? There are three types of current. If it is balanced system, then there will not be any current flow through the neutral. Neutral current will be zero. But if there is any unbalanced system, then there will be zero sequence current flow through the neutral. And that zero sequence current, they have the same magnitude, but there will not be any phase difference. So that's why that is just 3 times. So that is the meaning of this, 3 I naught, 3 I naught. This means IA plus IB plus IC is 3 times. So therefore from there you can write I naught is 1/3 of this. So why it is done? Like as I said, as I was telling her that A phase, B phase, C phase, 3 phase is converted into only 2 components to make similarity that, okay, there is A phase, B phase, C phase. In the side also there are 3 quantities, ID, IQ, I0. So that's why that engineer part, later he said, no, not only just 2 components, D and Q, let's relate it with the zero sequence component, which is I naught. So then it looks like right side I have IA, IB, IC in each and every equation, and then left side I got 3 components, ID, IQ, and I0. Accordingly, you see the title goes DQ0 or the Parkes transformation. So everybody now, could you understand?
Yes, sir.
Yes. So what is the meaning of this DQ? So now if you read many literature, you may not find in your assigned papers, but if you read many literatures, many journal papers, or if you see many books, frequently you will be getting this thing, DQ0. Especially if you study any article, journal article or conference article about transient stability, steady stability, frequently you will be getting this term. So this is used because this is helping me. This is making my calculation easy. I am able to make it time independent. Only in the equation I will have the theta. And then it is the simple 3 quantities, ID, IQ, and I0. That's why this system is very popular. So, I mean, there is kind of similarity. So everybody, can you remember that what is called the Laplace transformation in the circuit theory, Laplace? So what does Laplace do? So in case of the Laplace, that is time independent. They are the function of S only. This means if you have a time domain circuit, AC circuit, first you convert into Laplace domain or the frequency domain. What is the goal of that? That will be the function of symbol S only. And then at the end, again you convert back into time domain. That is what you do, and that is the beauty or essence of that Laplace transformation. Same thing, what is the significance or what is the essence of this system? It makes time dependent system into time independent. It is only dependent on theta, and that makes my life easy. And then I will be calculating a huge network problem with the help of DQ0 component. At the end, I can convert back them into the time dependent function so that I will not be ended up with multiplication or other thing. You see, like really these will be difficult to handle if it is time dependent, cosine omega t, sine omega t. When it is power and you need some multiplication, cosine square omega t, sine square omega t. So it will be huge and huge trigonometry. It is not like that you cannot do it, you can do it, but it's very, very difficult and complicated. That's why to analyze a 3-phase system, Parkes has invented the DQ0 method. That is the significance, and that thing we are looking, and I mean that gradually we'll be looking. Now everybody see, these 3 equations will be your concentration. So from these 3 equations, what I can summarize on the left side, ID, IQ, I naught, and right side only I, IB, IC. Now look this one, everybody see, DQ0 transformation. So from that on, from that portion, I just derived this one. You see, ID, IQ, I naught in matrix format, here I, IB, IC, and then those component, cosine component, those minus sine component. And you remember that here it was, last one was 1/3 IA, IB, IC. So that's why I wrote it here half, 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 and then 2/3 here, so that the meaning is the same. 2 will be cancelled, and it will be ultimately 1/3. So therefore, this is called the DQ0 transformation. So what it is telling you, what information can you obtain from here? This means, you see, this is just 2/3, and these are the, if you just know the theta, then this will be just some number. And now if you know IA, IB, IC quantity, then you just apply this matrix. Directly you are getting ID, IQ, and I0. So meaning that to analyze a system, for example, you are solving a huge network problem for any branch or for any specific location. If you just know, the same equation thing goes for the voltage also, the same expression. I mean, we are analyzing with the help of current, but the same conclusion goes for the voltage as well. So therefore, for example, if you know these things, then you just apply this one, that will convert you, that will give you those three quantity. And then you solve everything using these three quantity. At the last, again, you invert, you see, the inverse transformation. Therefore, I think many times you did the similar things, that you have a matrix, invert the matrix. This means left side it was ID, IQ, I0, and then when you want to convert back into IA, IB, IC, so I am writing IA, IB, IC. This is the inverse matrix of this one, and then ID, IQ, I0. This means that now if you know ID, IQ, and I0, you are analyzing, you got those three quantity. Now plug in those numbers here, and with the help of this matrix, then you will get back to that IA, IB, and IC. So that's why it is called the inverse Park transformation. And this is called the direct Park transformation or DQ0 transformation. Now, let's give you an example that where is it used. So because these days you are reading your papers, so it will really help you. If you just see this one, that application of DQ0 transformation for control of STATCOM. So you all know the STATCOM is static synchronous compensator. It is basically a reactive power compensator. And the STATCOM circuit, that DQ0 transformation is applied. This is very standard configuration. So therefore, let's have a look. What is that STATCOM? And at the beginning, everybody looked at just the first line, the online diagram. This means that, or you have the line, for example, generator three-phase line, and then you need a transformer, so Y delta transformer, and then there is on voltage source converter, and there is DC link capacitor. Therefore, essentially, this DC link capacitor and voltage source converter, this actually constitute the STATCOM. So this is the STATCOM structure. And of course, you need a transformer because you have to reduce the rating. For example, here it might be 11 kV or higher voltage, but these components cannot operate more than like 6.6 kV. That's why you need to reduce their voltage magnitude. That's why a transformer is used. So you can say this whole thing is a STATCOM unit, but essentially this voltage source converter together with this capacitor, this is a STATCOM. So now the thing is that how the control, how the control system for this STATCOM works with the help of the DQ0 transformation. So that is the thing. So you see what thing being done from here, from three-phase system, you see VABC. So when it is VABC, means this is the three-phase quantity, and that is the time domain function. And then it is giving into PLL, means phase locked looped, phase locked looped. And then just to find out the phase information of those three-phase quantity. And then So this means that PLL will give you the angle theta. But can you see it is added pi over 6. Pi over 6, how much is that? This is pi over 6, 30 degree.
30 degree.
Yes. Why is it used? Because there is an Y delta transformer. Probably you know that in case of Y delta or delta Y transformation, there is a phase shift of 30 degree between this side quantity and that side quantity. So keep in mind, if it is YY, then phase difference is 0. If it is delta delta, then that is also phase difference 0. Whenever it is Y delta or delta Y, then there will be always 30 degree phase change. That is the rule of the transformer. So accordingly, there is pi by 6 and that has been minus, has added. So then that is your theta. And why theta is calculated? Because you know, in this transformation, either direct DQ transformation, you need the theta, or even in the inverse transformation, you need to know about the theta. So that's why that theta is being detected with the help of phase lock loop. And then you see where it is going. What is the objective of this block? ABC to DQ. This means with the help of this one, ABC, and then you are taking current from here, IABC. This means that three-phase current is coming here and you need the theta. So this means actually you are doing this thing. You got that IA, IB, IC from the line. You are applying theta. Now you just calculate. You will be getting ID and IQ. That is the meaning. So that's why DQ. So here you see that typically only it is converted into DQ. In most cases that I naught is not counted. So just these two is fine. As I told you that this thing has been placed just to make some similarity. Okay, there was three-phase system here. Why not putting three component here? But actually you see, here there was no zero sequence. Only there was D axis and Q axis. That's why frequently in control system, only it is converted into DQ component. Just keep in mind. So anyway, then you convert it into DQ, and then what it is doing, everybody look. I mean, you don't need to fully understand that how this is all. I am just showing you the application of that DQ transformation. That is my goal. So therefore, from here, this block, you see two component, the direct access component, ID component, and then IQ component. That thing we learned that ABC can be changed into DQ component. And then from here, you know, the control, there is controller, control block diagram, something is coming from here, something is coming from here. And then there is another control block, it is going. And then here it is although the current component, but once I am combining with these quantities, you can say this is the voltage quantity. So therefore, for example, I got VD and VQ. Then, but actually I have placed the STATCOM along the line. So along the line, I have that three-phase system. D and Q is not there. So then ultimately I have to wind back to the ABC. That's why you see that VD and VQ, again it is going into that DQ to ABC transformation, meaning that you have to make the inverse transformation. That is being done. And then again you need the theta here. You see, in this equation also there is theta. That's why again that theta is coming from here. I mean the same thing, this theta is going there and this theta is going here also. And then what you got it? You got from DQ into ABC, actual component. And then you apply that PWM, pulsed width modulation technique. It will produce 6 pulse and it will trigger the 6 IGBT or 6 GTO gate turn off thyristor or insulated gate bipolar transistor, which are placed inside the VSA. That's why I said, I mean, you may not need to understand this thing. Just you see the application of DQ0 from first ABC is converted into DQ, and then here again it is inverted from DQ into ABC. That is my goal. So this means that, as I mentioned, in power system stability studies, frequently this spark transformation or DQ transformation is used. Even in most of the control system, if you look induction motor control, other sophisticated control, frequently this DQ transformation is used because that is easy to handle. You see, I mean, this portion is the main controller for this STATCOM. This thing is the line, but you know that EDC voltage is coming from here, and then VG reference is coming from here, and then these are the control block. There are two PI controller, another two PI controller. This is the main control block, but in the control block, I am using those ID and IQ because ID and IQ is just the number. They are not time dependent function. So therefore, until this point, this means the main control algorithm, control theory is based on the D and Q. But then finally, I have to convert back into time domain in order to apply in the PWM technique. That's how I am doing there. But the main control thing, because actually you will be tuning these parameters, and this is very time consuming task. At that time, don't use any time domain function, use just some numbers. That is the objective of changing from ABC into DQ. Everybody, could you follow me so far what I'm saying?
Yes, sir.
Yes. So therefore, from today, everybody, as power engineer, you understand the meaning or the significance of the DQ0. Now, as the days goes, if you read many literature, frequently you'll be getting DQ0 or the DQ. Or you are listening someone's lecture, frequently they'll be using the DQ, or sometimes parts. That time you will concentrate. That is basically these things.
Dr. Ali,
Okay.
I have a question.
Okay, sure.
So we are using DQ transformation just for controlling purpose here, because if you see PI controller 2, so that is, I'm just being used there, right?
Yes. So as I said, that for this STATCOM, like this is the main control block, this portion. So therefore, and then this PI means PI number 1, PI number, these are called the PI controller, proportional integral controller. And there are two here also. And here you see that something is coming from here, but then here you need on D component because you want to control this one, somehow you need the information of the line. But from the line, we will not directly give the time quantity. That is the meaning. That's why in the controller, instead of giving any time function, let's convert that ABC system into DQ, and then you give those currents.
Okay, thank you.
Got it? Yes.
Yes.
Therefore, you will see, and I mean, for example, the Morteza does, or in the past Mahfouz does, or many other researchers, or in their paper, as the days goes, if you read, frequently you will be seeing these things, ABC into DQ or the DQ to ABC, just to make ease of the calculation. It will make your life easy. That's the
Right.
yeah.
Right.
Okay, great. So now moving forward, everybody see this slide. This slide, the title goes synchronous generator parameters. Synchronous generator parameters. Now you know that synchronous generator stator has the coil, and we already discussed it has the inductance, and then rotor circuit, it has the magnetic field or the magnetic coil, and that is also inductance. But you see here the extensive list of the various parameters. So, and then those parameters are frequently expressed in terms of the direct axis and quadrature axis component. That is the reason I am showing you this table. So for example, what are the parameters? Stator resistance, RA. So therefore, definitely everybody can see, because these are the coils, they have a small resistance, although mainly those are inductance in nature, inductive in nature, but they have a small resistance as well. So that is the meaning. Stator resistance, RA. One thing is that right side the unit, you see, I have written few. So probably you all know few means the per unit system. I mean electrical quantity. I mean what should be the actual unit here? Stator resistance RA. It should be ohm, right? So you all know. So therefore, instead of writing ohm, every quantity is expressed in terms of per unit, and some quantities are expressed in second. I'm coming that point later. So the benefit of having the per unit means per unit definition is actual value divided by the base value. For example, you got a 100 ohm resistance value. So instead of writing that 100 here, you assume a base value. For example, your base is also 100. So 100 divided by 100, you will get only small number, which is 1. For example, in a big network, you will be dealing like several thousand volt or like several hundred current. Therefore, those will be big numbers, big numbers. You want to calculate power, then again it is going very big number. Even though you convert into megawatt or kilowatt, but still those will be big number. In order to avoid those big numbers in power system, there is a system which is called per unit, PU. So what is the definition? Actual value divided by base value. So for example, you can say, I mean, many times in the literature or article, you will find the generator rating. For example, there is a generator, it says its rating is 1.5 per unit. What does that mean? Is that 1.5 it is only watt or only it is megawatt? No, that is in per unit. So therefore, for example, you have a 30,000 MVA or megawatt rating generator and your base is 10,000 MVA. So this means if you divide 30,000 by 10,000, then result is 3. That is the meaning of per unit. Everybody, do you understand what I'm saying?
Yes, sir.
So you all know about this per unit thing?
No.
No?
Mhm.
Okay, so let me, just a moment. Let me take you momentarily to that whiteboard. So we are discussing that it is called the per unit, which is briefly called the PU, which is briefly called the PU system. So therefore that, okay, so let me write. So therefore that PU, that equals to actual value divided by the base value. That is the definition. Per unit actual value to the base value. So then what I am saying, for example, you have a line and then these are the line, this is R and then this is L. Then for example, in the line, this is 300 ohm and then this is also, for example, 500 ohm. I'm expressing in terms of reactance or impedance. These are the value. And then for example, you have a generator and then you said, okay, this is like 30,000 MVA. It is expressed in that way. And then its voltage is, for example, that 11 kV. And then I said you, okay, this is the system. Okay, the find out the current. And then after finding out the current, find out what is the power loss. So therefore, definitely you see, oh, of course you can calculate, but can you see the number? This is 30,000 MVA. This means 30,000 multiplied by 10 to the power 6. This is 11,000 volt. And then these are the number. So therefore, you see the current value will also be big. And then once you will calculate the power here, that will also be the big value. And then this is just the simple circuit. Think about the hugely interconnected system. So as you go upwards on the system, power flow calculation, then there will be lots of multiplication, division, and then those will be huge number and huge number. And also it is always difficult to express what should be the unit. You see, for example, you will be dividing this one by this one, then that will be current unit is ampere. And then again, if it is a hugely interconnected system, the other lines are going on again. For example, there are tapping from here and here, and you are asked to find out the voltage or current in that branch. So therefore it is very, very difficult, and then the numbers will be huge and huge. That's why in order to avoid those long or huge numbers, the per unit system has been established. So what is the definition? Actual value to the base value. Therefore, for every system, typically the MVA and then the voltage rating, their base ratings are defined. For example, assume that for this system, the base is 10,000 MVA. That is my base. That is the base quantity. Base means kind of the reference thing. That is my base. And then say also I said 11 kV is my base. So if that is my definition, so everybody's, what is my per unit definition? Actual value over base value. So therefore, what is the actual value here? 30,000. What is my base value? 10,000. So what is the result here? Just the 3. So you can say generator rating is 3 pu. Now see this number is pretty small. Similarly, how you can express voltage? What is the per unit value? Just 1. So you can say I have a voltage of 1 per unit. Similarly, for these things you have to consider the base. For example, your resistance base is 300 ohm. So therefore 300 by 300, just 1. And let's say its base is 500, so 1. So now you see the number, it is 3, it is 1, it is 1, it is 1. Now it is much easier to calculate even the much bigger network than having these actual big numbers. And then once you get the number, for example, you are trying to find out the power of this branch and you got the result, okay, it is 3.2 per unit value. I got this number after manipulating. So then what will be the actual value? Then use this definition. What is your actual value? Per unit multiplied by what was the base or what was my reference. Then at last you will get the actual value. But inside, you are able to deal with very small number. Those are called the per unit system. Everybody, could you follow me what I am saying?
Excuse me, sir.
Yes.
Sir, how we assume the base value based on the circuit?
So you will be looking typically, for example, in the power operator or power system, they have a huge map of this type of system. And then they define those numbers. Now, for example, for your case, you can choose any number. For example, in this case, even you might choose, okay, I will be choosing 30,000 as the base. Why I will be choosing? So that my result is 30 by 30 becomes the 1. So it depends on the typically what is done. What is the rating of the voltage that is available at the terminal? That number is considered as the base. And a good number, like for example, in this system, I have drawn only one generator, but there can be many generators in an interconnect, like all are connected. There are other generators. So first you look the rating of all generators. For example, this could be only 10,000 MVA, just an example. This could be 20,000 MVA, but this one is like 30,000. So now based on that, you make a good decision that which number you should consider as a reference or base, that in all cases you will get a small number. That is the thing. So therefore, for example, if you have here 20,000 MVA, this is 10,000, this is 30,000. If you assume that, okay, 30,000 is my base, the biggest one, then you are getting 1. And in this case, you will getting a small number. For example, 0.2, 0.8, that is also fine. Still, those are the small number. So, do you
So the
understand?
terminal voltage is considered as the base voltage, right?
Yes. Terminal voltage. Typically.
So that base value is applied to the entire circuit, like the resistance, inductance.
For the calculation.
Yeah,
This
that's right.
the
For the
per unit
calculation.
system is just for the calculation purpose. That is not the real thing. You,
sir.
you have a real power network. Now you need to analyze the voltage current for a hugely interconnected system. That time, at first you convert into per unit quantity. And then once you get your desired value, whatever thing you are finding out, then at last you convert back into actual thing. So the meaning is the same. You will be getting the same result. I mean, if you deal with these huge number, if you are able to do, you do. I mean, it is not like it is impossible. You can do, but very, very complicated. Always you will get in your calculator huge, huge number. But if you go with this number 1, 0.2, 0.5, and always those are the number throughout the network, then that is much easier. So therefore, per unit system, just for the sake of the ease of calculation. Is this fine?
Yes, sir. Thank you.
Yes. So everybody, what I would recommend you all, everybody, today after the class, you Google per unit, PU. PU. So therefore, and you will see if you Google, there is on like for voltage, in case of the voltage and the MVA, it depends on the system operator or power engineer's experience or whatever value you want. But typically for the impedance, I mean, the way I did, they don't do that. So there is one standard thing. Let me write down, then you will be getting. So, sorry, or let me use this one. So the base impedance equal to base kV squared, base kV square over base MVA. That is the definition for the base impedance. This means what was your base value? 11 kV. Now let me go back. For example, that 11 kV is squared over what was my base? Like I assume 30,000. That is the definition of the base impedance. So therefore, if you Google, if you read any literature, after defining the base value for the MVA, after defining the base value for the terminal voltage, then literature immediately does what is the base impedance. That will be used throughout for any component, resistance, inductance, or capacitance. This is the thing, base kV square over base MVA. Then as you can see, still you will get a small number. That is the definition of the base impedance. So therefore, everybody, I recommend you after the class, you all please look the literature, or if you have a book, you look the per unit. What is the per unit system? So it is frequently used in power network to analyze a system, because you can easily and you see, because it is the other you see advantage is that not only the ease of calculation, because it is per unit, so you are not worried about what is the unit. It is ohm, or it is ampere, or it is MVA, or megavar. You are not worried. Everything is per unit. I mean, just the number. Do you understand what I am saying? Everybody, could you follow me? Yeah. It's just a number. Like 1 per unit means 1.5, just number, just a number. That is called the per unit. So that's why, I mean, based on that, now go back to that slides again. That is the reason, you see, everything is expressed in terms. This is the realistic situation. I mean, real power engineers, I mean, they have the real values, but for the analysis purpose, they frequently express the quantity in terms of per unit quantity. So that's why we are looking at synchronous generator parameters. What are the parameters? Stator resistance, Ra, unit per unit. Stator reactance, Xa, per unit. After that, you see, it started like direct, and then quadrature. Everything is expressed in terms of the d-axis and q-axis. So direct axis synchronous reactance, quadrature axis synchronous reactance, XD, XQ. Direct axis transient reactance. So you all know the transient, subtransient, and steady state value, because there might be any transient happens in power network. Accordingly, those reactance value change. So that's why direct axis transient reactance, XD prime. Quadrature axis transient reactance, XQ prime. You don't need to memorize this thing. Now Manoj and then everybody, if you click the Simulink, I mean when you are at home or in the lab, and then everybody open the synchronous generator module, and just you copy and paste in a file. And then if you click that component, then it will take you the parameters, and then you will be seeing these symbols. This means that at least in Simulink or MATLAB, synchronous generator parameters are represented in this format. So therefore, and then you will get direct axis subtransient reactance, XD double prime, quadrature axis subtransient reactance, XQ double prime, direct axis transient time constant. So these three are the time constant. That's why unit is second, second, second. And then the last one is inertia constant, H, which is also second. So today I will be discussing about this inertia constant. I mean, these all are the parameters. Of course, these parameters have a dominating role in determining the stability of the system. But among all those components, inertia component is very, very important. It has huge impact on the system stability study. So we will be looking that thing. What is that inertia constant? And you see that inertia is coming from the rotor shaft, because of its movement. And then you know that inertia is related to the mass or weight of a body. Therefore, when it is moving, of course, it has some weight and mass. But once the rotor is moving, it is gaining or it is storing some kinetic energy, right? Because it has a velocity, it has a mass. So by the equation half mv square, it is gaining some energy. And that inertia constant is related to the machine rating and with that stored energy. So therefore, let's have a look at definition of the inertia constant. Everybody see? What is my definition? H, stored energy at rated speed in megawatt second. Because you know this is energy, so this means power multiplied by the time, so second, divided by MVA rating. So the thing is that typically in real practice, in real world situation, if a machine has higher rating, for example 1000 MVA, then its H value is higher. And if the machine rating is lower, for example 10 MVA, 2 MVA, H value is lower. I mean, it is not directly proportional. I am not saying that one, but kind of it has very similar to linear relationship. With the increase of the machine rating, H value increases. With the decrease of the machine rating, H value decreases. And that H value has huge impact on the system stability. So therefore, everybody see that is my definition of H. And what I wrote, what is the stored energy? Stored energy is the kinetic energy. And what is that kinetic energy? You all know half mv square, but in this case, instead of the m, it is used j. What is the j? Moment of inertia in kg meter square. And then omega naught m square, that is the speed. And that speed is the rated speed of the machine, which is the shaft speed actually for synchronous machine. So therefore you see, and then that omega naught m rated speed in mechanical radian per second, which you can say 2 pi rpm over 60. Now plug in this kinetic energy in this equation, in the top equation H. Substitute the kinetic energy for this one. If you do that, then that is going there, and then you change omega naught m with this one, You put that on, and then omega, and then you keep going, you convert, and then once you put that on, put the pi value and everything and 60, then you will get this result. H is 5.48 10 to the power minus 9 J RPM squared over MV rating. You see, after putting in this one, and then because that is getting squared, so after manipulating, you will be getting this one. So everybody, please write down the last equation in your note. Please write down that H equal to this thing. Right now you note down. I mean, soon I will be discussing on numerical problem. Then that time you will need this equation. Is everybody fine?
Yes, sir.
Yes. Everybody, do you have your calculator?
Yes, Dr. Ali. I
Does
do have.
everybody? Sindhuja, Lakshmi, do you have calculator?
Yes, Doctor.
Yes. Everybody.
Doctor.
Amani, please, do you have calculator?
Yes, Dr. Ali, I have.
Okay. Okay. So therefore, before going to the next slide, can you please write down this equation, the last one, just the last one. You just write this on that H equal to 5.48 10 to the power minus 9 J RPM squared over MV rating. And then see the meaning. J is the moment of inertia in kg meter square. And you know that RPM is revolution per minute, which will be the generator speed. And you know the MV rating, that is the generator or machine rating. Are you all done in writing this equation? Then I am scrolling down the second slide. Next slide.
Yes, Dr.
Everybody done?
Yes, sir.
Yes.
Okay.
Yes, sir.
I mean, again, because I have already uploaded, and so again, you'll be looking video, so you can see, you will not lose it, but okay. Now everybody see. Now read the problem. I have set up some problem for you that you have to do using your calculator. So see, the inertia constant of a 2-pole 60 Hertz synchronous generator is 2.5. If the reactive power supplied by the generator is 400 megawatt, then calculate the system power factor provided that the moment of inertia of the machine is 27,500 kg meter square. Because you know it's a huge machine. That's why I have used this big number. So the inertia constant is given that in the equation that you all just wrote down, the H value is given, which is 2.5. And then this is the synchronous generator rating or information. It has 2-pole 60 Hertz system. And what else given? Its reactive power information is given, which is 400. So based on that, find out the system power factor. What is the power factor? Provided that the moment of inertia is this one. So this means this value, this number is for that J. So therefore what you are getting, your H is given and then your J is given. So therefore everybody, if you see this equation, H is given, J is given. So MV rating is not given, but is RPM given? RPM, read the statement. Is RPM given in any way?
No, we can calculate from 120 FYP.
Exactly, exactly, yes. So everybody see from this information, 120F over P. Everybody, please write 120F over P. So therefore, everybody see, just a moment. For a moment, let me take you to that, and then again you go back. Let me clean up all of those things. I just write down one thing, and then you will be fine. Okay, so you need two things. What is the synchronous speed? Synchronous speed is 120f over p. You need to use this one. That is basically the RPM, revolution per minute. So from this equation, you will be getting that one. And also you need to understand this one, because question is to find out what is the power factor. This is theta. So you see, this one is the real power. This axis is the reactive power. And this axis is the apparent power, which is this one. Therefore, everybody please write down this triangle in your note. Then you can find out the power factor. So therefore, for example, from this power triangle, what is that power factor? Power factor is that cosine of theta. This is cosine of theta. What is the relationship? Phi over S. This means P is that real power. This one is that real power. Sorry. And then this one is that reactive power. This one is the reactive power. And S is that apparent power, which is expressed in MVA. Therefore, this quantity typically expressed in MVA. This one is expressed in megawatt, and this one is expressed in megawatt. So therefore, this is one thing. Power factor is this one. Or if you know the real power and then the Q, then also you can use tangent theta from this triangle. What is the tan theta? Q over P. So if you can know this one, then you will be getting theta first from this one, and then later convert into cosine theta. Just if you get theta, then that is also possible. So everybody, you just draw this power triangle in your note and designate these symbols, and you need this n equal to 120 f over p. From here you will get the revolution per minute for the generator. Then you are fine. So everybody is fine. Could you follow me?
Yes, Dr. Ali.
Okay, very good. So now I am going back again, that slide. Now see, the inertia constant, this on. So therefore that I said, in the equation, your H is given, your J is given, your RPM is given. So, I mean, you have to calculate from 120 F by P. So therefore, what you will be getting? You will be getting your MVA, right? From this equation, you will be getting MVA. So therefore, once you get the MVA, and then your M bar is given. So therefore, I mean, you can make a relation with that by applying the sine theta. Sine theta is that 400 over that one. But you also, once you get that MVA, and then with the help of that S equal to root over P square plus Q square, then use that one, that will give you the P value. And once you get the P value, then you can find out the power factor. Therefore, it's just the trigonometry. Whatever way you go, you just use that power triangle and then find out the power factor.
Dr. Ali, is it 0.89?
Sorry? How much you said?
Is it 0.89?
Yes, looks pretty good. So, Manoj, how much you got? So, Amani, what was your MVA value?
I got 781.2.
MVA value, you said 700?
Yeah, that's MVA value. Yes, it's MVA value.
Just 700?
781.2.
Just 700?
No, 781.2.
Oh, 702.2. Then Manoj, how much MVA you got?
I got the same one.
Okay.
So 781.22.
Okay. Then now using that MVA, that now you see the power triangle, that MVA value, that is the S value in the power triangle, apparent power. S equal to root over P square plus Q square. Now you see in the statement, in the second line, the reactive power is given 400 megawatt. That is the Q value. So therefore, if you use that S root over P square plus Q square, and for S you put 781.2, for Q you put
So
400, then you will be getting P value.
I got 0.85 power factor.
Oh, so there is
I
little.
got 0.89.
Okay, who said that, Lakshmi?
Yes, Dr. Ali, I mentioned earlier I got 0.89 power factor.
Okay, so it looks like there's a little bit difference in between 0.85, 0.89. Lakshmi, did you calculate the P value, real power? How much was that?
Yes, Dr. Ali, it's 781.2362.
No, that is the MVA value.
Yeah.
That's not the.
That is
Yeah.
the S value. I am talking about the P value, capital P in the power triangle, the real power value in megawatt. So to know that, you have to find out S equal to root over P square plus Q square.
Actually, I use the sine theta equation, so we don't need to calculate the P.
Oh, okay. So
Yeah.
oh, okay. So this means you use the Q and S, right?
Yes.
Okay, sine theta. And then once you get the sine theta, then you have to convert into cosine theta.
Yes.
So therefore, Manoj, ultimately you said you got 0.85.
Yeah, I just, I mean, didn't write anything down in the paper, so I just use the calculator. Maybe
Oh, no,
I might have some flaws. So.
Okay. So then, Lakshmi, so did you also use the same method? You use the Q and S to calculate the sine theta first and then cosine theta?
Dr. Ali, I used P first and then calculated S, apparent power, and from that I calculated cos theta, P by S.
Then could you check your calculation once again? Is it 0.85 close to or 0.89?
Okay, Doctor, I'll check one more time and let you know.
Yes. Because I mean, I am understanding that it's close, but still there is like a little difference. That should not be the difference. Anybody else? Did you calculate?
I got 0.86 for power factor.
0.86. So Sindhuja, you said that one? Who said that one?
Amani.
Money, I think.
Oh,
Amani.
sorry, 0.86. Okay.
Yeah, that's what I got, like 0.858. That is pretty much 0.86.
Yes, I got the same.
Yes. Therefore, Lakshmi, please check once again. Yeah. I mean, you are not much deviated, but it should be pretty close, around 0.85. Venkat, Kamana, are you everybody doing?
Yes, sir.
Yep. Please keep going. Just you need that H equation, you need N equal to 128 over P and that power triangle. Just you need these three component and then you can find out the power factor.
Dr. Ali, I'm getting the same 0.89.
Really? Yeah. Okay, so probably it is then some calculator truncation or the rounding issue probably.
Yeah, maybe I'm taking 4 or 5 digits after the point, so maybe
Okay,
that
that may, yeah, that may affect, yeah. Okay,
yeah.
okay. So then, Sindhuja, are you doing? Sindhuja, could you hear me? Maybe she is not connected.
Yeah, she is not there. I cannot see her.
Oh, maybe there
Yeah,
is.
she left the site.
Oh, okay. That's why she is not responding. Okay. Anyway, Venkat,
Yeah,
Kamana.
Yes, Dr. Lal, I'm still calculating.
Okay. I
I'm
mean,
working.
Kamana and Venkat, you understood the process, right? Yeah.
Yes, yes.
Yeah. Okay.
Yes, sir.
Just the matter of calculation. Yes. Okay.
Yes.
You see, because of this, Zoom system, I cannot see you likewise the way we teach in the physical class. So it's something different, but it's still with the help of the pen, paper, calculator. So you have to do in that way. So after this class, what I am going to do, I am going to assign you the first set of homework. Okay. So hopefully by tonight, first I will be uploading the first set of homework, and then I will be sending you an email. And then due date will be next Thursday. I mean, September 10th. I mean, you will be noticing some similar problems and some short questions. So is everybody fine with that?
Yes, Dr.
Yes.
Yeah, September 10th
Yes, sir.
will be deadline. I mean, the next Thursday. I know that you have long weekend. So I will not say the deadline is coming Tuesday. So deadline is Thursday. And then right after that in another class, I will return you because I think you will have your first midterm exam probably September 22 or September 21st. I forgot. Probably around that date. So once you return me, then immediately I'll be looking and I'll return you and I'll discuss in the class the answers. Oh, Othman, are you there or you left?
I'm here, Dr. Ali.
Oh, so are you calculating?
Yeah, Dr. Ali, but I got lost in the middle, so I'm recalculating.
Oh, okay.
Yeah.
Okay, therefore those who are done with the first one, just you read the second problem, like Manoj and then Lakshmi, Amani, you read number 2. And can you do that? Number 2. I mean, today we don't have time, but you just think number 2.
Yes, sir.
Manoj think how to do that number 2.
Okay, first I
Yes,
think we
Doctor.
have to
I'm looking
confirm.
at it.
Yeah.
We have to confirm the horsepower first, I believe.
Yeah. So you have to make a relationship between horsepower and then torque, Newton meter.
I think horsepower is torque times RPM over 5,252.
Okay. So therefore from the horsepower, now horsepower you have to convert into watt. by
746 watt.
right. So therefore that power is torque multiplied by the speed in radian per second.
Yeah.
Therefore,
So
from there you will be getting that speed. So once you get the omega, right. So once you get that information in radian per second, then you have to convert into RPM. And then you see the rest of the information are given very similar to number one. And then again, the same question, find out the power factor of the generator.
Right.
Okay. Anyway, so just you do, and then next time we will discuss. Today we don't have much time. Lakshmi, are you fine?
Yes, Dr. Ali, I'm trying second problem.
Yeah. So therefore, just we discussed, I'm giving you the hints.
Yeah, I just followed them.
Yeah. So horsepower you have to convert into watt. That will be the power. But then the torque, actually that synchronous motor is the prime mover for the generator. So this means the synchronous motor shaft is the same shaft as the synchronous generator. You need to know the shaft speed in terms of RPM. That is the thing. So you have to make a relationship between that horsepower and torque and the speed. So the formula is phi equal to torque multiplied by the omega, where P is in watt. P equal to torque multiplied by omega, and omega is in radian per second. So, and then torque is in Newton meter. So from there, once you get the omega, but that is in radian per second, you have to convert into RPM. That's the thing. Meaning that you have to multiply by 60 and you have to divide by 2 pi to convert radian per second into RPM. Then that is your RPM in the H equation. Again, you need to use the same H equation that you did in previous problem. And then you need the help of that power triangle and then see rest of the information. And you are fully fine. You will be able to find out the power factor.
Yes, Dr. Ali, got you.
Yeah, okay. And then as I mentioned, like you please watch out and by tonight I'll be setting up some question numerical problem for the homework. I will be uploading in the e-courseware, in the class page, class content page, and then I will be notifying you.
Okay, Dr. Ali.
And I will be creating a Dropbox, like for example, in the assessment tab, homework set on. There you all will be uploading your homework by the deadline. There will be a deadline, that is September 10th.
Okay, Dr. Ali. Sounds good.
Okay, then Kamana and Venkat, like you keep going. You try your best at home and see
Yes,
that you got that similar result, 0.86, 0.85, or as Lakshmi said, close to 0.89, whether you are getting your power factor in that range or not.
Sure.
Okay.
Sure.
Okay. So please, you keep going. So